A big welcome back to the class of 1973 and everybody else who's joining us this morning to participate in the 50th reunion alumni seminar, Changing the Course of Climate in the Next 50 Years. As some of you may have realized, I'm not Michael Jones, class of 73, but I am Hank Art, Rosenberg Professor of Environmental Studies and Biology Emeritus. And I came to Williams as a freshman faculty member during the class of 73's sophomore year. So I know some faces and am looking forward to greeting others. The topic that the 50th reunion class has chosen is one of the most urgent and perhaps the most urgent in the entire history of the human existence on this planet. But it's only recently that we have realized it as such. Back in the early 1970s, the population bomb and toxic pollution to air and water were the major threats seen to the biosphere. And they were elements of what we then called the environmental crisis. So it wouldn't be a Williams College event if we didn't have some data, at least not a science event. But the perfect transportation envisioned back in the early 1970s was a vehicle that had only water vapor and carbon dioxide coming out of its tailpipe. That's not what we envision today. There wasn't even a consensus on whether the planet was warming or cooling down or neither. And this is a bit of data which shows, if I can, wrong button. Here we are in the 1970s. These are the numbers of articles published, and look how few articles were being published per year at this time on the future global warming, cooling, or neutrality compared to the 1970s. Well, 1965. And the trend line in red is warming, the trend line in blue is cooling, and the yellow line is neutral, that these papers claim that there wasn't going to be much change at all. So look at here. Your freshman, sophomore, junior, even senior years, there really wasn't a consensus, and lots of people thought the climate was going to be cooling because of all the particulates in the atmosphere at that time. So, and we can address that, or the panel can address that further this morning. Reflecting back on the early 1970s, it's hard to imagine that we missed the changes that would occur over the next half century. We undoubtedly now all have our own personal stories reflecting back on how the world has changed over the last half century since you were undergraduates at Williams. And mine personal reflection, in which I smacked my head and said, oh my God, things are really different, actually dates back to my PhD work that I did on Fire Island off the south shore of Long Island in 1967, studying an ecosystem called the sunken forest there, and set out all of these plots, 35 plots. And here's the Great South Bay, Long Island up on the ceiling, Atlantic Ocean down here. And I, over the years, followed that. And this is, oops, one second. And this is the way it looked in 2013. I had lost 20% of the plots that I had set out on this barrier island. And one of the plots was actually in the Great South Bay, due to the rise in sea level along the Atlantic coast. So I'm sure you have your own stories and reflections. No longer are we arguing whether humans have had a role and whether the climate is changing. 25 years ago, that was a constant discussion. And there was a December 2022, a Yale program on climate change had published data on the 6 American views of the changing climate. And they range from people who, when questioned about climate change, were alarmed, 27%, concerned, 26%, cautious, it may be happening, but well, let's wait and see, 17% disengaged, I really don't care, was a smaller wedge, 11% were doubtful, and 11% dismissive. So evidently your class was polled about your attitudes. And this shows the value of a liberal arts education, I think. 3/4 of you were alarmed, and another 16% concerned. So, you know, it shows just how great the capacity to perceive the environment is on the part of the class of 73, and I'm sure other Williams College classes show the same. So this morning we have assembled a panel entirely drawn out of people who have either now or in the past been involved with the Center for Environmental Studies. And they include, from left to right, Thomas Jorling, who was the director of the Center for Environmental Studies and taught many different kinds of courses while he was here, and then later became the Commissioner of the Environment of the Department of Environmental Conservation in the state of New York. William Moomaw, formerly of the class of 58. So he's reuniting too? Is that right? You're reuniting right now? 58? You're not?
59.
I wonder why it said 58. The alumni office has made a mistake. I copied this directly off their website. 59. Well, this young man who's not as old as those in the class of 58. Formerly of the Williams College Chemistry Department and also a director of the Center for Environmental Studies. And then went from Williams to Tufts, where he was involved in the Fletcher School for International Studies with their environmental program there. And has more to say on climate change probably than any other human being in this room. And then Allison Gill, currently of the biology department, and who is doing research out in the Hopkins Forest on carbon dioxide, carbon and nitrogen cycling through decomposing communities. And Mia Cook of the geoscience department, and the Environmental Studies program, who's long taught the introductory course in environmental science, and I guess Allison has as well, as has everybody here but Tom. And they are our panelists who will have some comments in response to a preloaded questions that have a very short presentation each. And then that will be followed by a roundtable discussion. And then the floor will be open for your questions, comments, and observations. My role is to keep the program flowing and end on time, even though we didn't start on time, and finish around 11:15. So welcome, and let's look forward by first probably looking backwards and seeing how we can drive by looking in the rearview mirror. Okay. Let me get the questions out. So the first question is directed to Mia.
You need the mic.
Oh, I'm sorry. The first question is directed to Mia and is, how does our current period of global warming differ from past episodes? And how do we know that most of it is man-made?
Hello, everyone, and thank you for the 50th reunion class for inviting me to participate in this panel. So in the slides here, I'm going to be showing a bunch of data. All these figures come from the Intergovernmental Panel on Climate Change report from 2 years ago. To start out, human activities have unequivocally caused increases in greenhouse gas concentrations. So on the left here, you can see data from Greenland and Antarctic ice cores. These are measurements made on fossil air bubbles in ice for the last 2,000 years, showing the concentrations of the 3 major greenhouse gases, carbon dioxide, methane, and nitrous oxide through this time. And human activities cause these gas concentrations to increase through extraction and burning of fossil fuels, agriculture, and also land use changes like deforestation. Since the Industrial Revolution, atmospheric concentrations of all of these gases have monotonically increased, gotten higher every year. In fact, this figure is from 2 years ago, and I've had to update it with the most recent numbers because it just goes up and up all the time. And we've known for over a century that these gases have properties that they absorb infrared radiation, which means that when they're in the atmosphere, they cause the atmosphere to trap heat radiated from the surface of the Earth. And this causes warming. And you can see that the rise in greenhouse gases is alongside clear warming that occurred during the 20th century. If we look back at this record of global average surface temperature through time, the Earth has warmed about 1.1 degrees Celsius since 1850 to 1900. And it's unequivocal that human activities that change greenhouse gas concentrations have caused this rise in temperature. So to put that temperature change we just looked at in context, if you look at the left-hand graph, the black line shows the observations of temperature. So these are actual measurements made with thermometers. And we can patch that together with reconstructions of temperature from the past. For the last 2,000 years, that mostly comes from reconstructions of temperature that come from tree rings and from measurements in corals. Tropical corals. And you can see that the temperatures that we're at right now are the highest they've been in the last 2,000 years by far. But then if we look further back in time, we can actually see that the temperatures today are greater than any temperature that has been recorded for at least the last 125,000 years. And another way that that's unprecedented is that the rise in temperature has been extremely fast. It's faster than any known climate change that happened naturally in the geological record. And we know it's caused by humans. One week we can verify that. Not only can we measure the properties of greenhouse gases in the lab, but we can also use climate models. So the most sophisticated climate models in the world, there are many of them built by many research groups around the world. They're similar to the models used for weather forecasting. We can put parameters in the model that we know change climate. And the 3 main ones are greenhouse gases, large volcanic explosions, which cause cooling of the Earth actually from the aerosols. And then also the third is how bright the sun is. And so if we keep greenhouse gases constant at the concentrations from the pre-industrial time and just let solar and volcanic variability happen, then you get this blue line here. And it really doesn't match the black line, which is the observed temperature change. You have to take into account the greenhouse gas changes caused by humans in order to explain the temperature changes that we see. So if we look way back in time, so this is what I do, I'm a paleoclimatologist, so I study how to reconstruct climate from the past and why it changed. This is 800,000 years of CO2 changes from ice core records. This goes back 10 million years and 60 million years. These are reconstructions of CO2 from measurements in deep sea sediment cores. And then these are temperature reconstructions from that same time. And what you can see is that the greenhouse gas concentrations we have today are as high as they've been. They're The last time CO2 was naturally this high was over 2 million years ago. And that's when, over multiple centuries, so when the climate has adjusted to that CO2 level, temperatures were 2.5 to 4 degrees warmer than pre-industrial. Okay, and that's with modern greenhouse gas concentrations. We have only warmed by 1.1 degrees because the climate system is still catching up. And so the paleoclimate can tell us what kinds of climates we can expect to see with greenhouse gas concentrations that persist at high concentrations for multiple centuries. And if you look at the relationship between temperature and CO2, there's a clear relationship. More CO2, more greenhouse gases mean higher temperatures.
Thank you, Mia. There'll be an opportunity to ask questions about what the panelists have said when we get to the question and answer at the end. The next question is directed to Allison. Global ecosystems currently take up around 50% of human emissions, dampening the rate at which carbon dioxide accumulates in the atmosphere. Deforestation and human development, however, reduce the strength of terrestrial and land carbon sinks and also contribute to biodiversity loss. What are some ways that changes in biodiversity might interact with and respond to ongoing warming over the coming decades?
Yes, thank you all for being here. So as Mia just described, fossil fuel combustion is undoubtedly leading to an ongoing increase in atmospheric CO2 concentrations. But one thing that's important for us to keep in mind is that only about half of the CO2 molecules that humans emit have historically actually ended up in the atmosphere. So this figure, the red line shows anthropogenic CO2 emissions. The blue line shows the contribution of those CO2 emissions to the atmosphere. And the other half of those emissions end up in land systems right now, as well as the ocean, with about a quarter of emissions going into each pool. And so collectively, global ecosystems have a very important role in buffering some of the externalities we could experience from ongoing fossil fuel combustion. And a piece that's important for us to keep in mind in this context is that many of the same activities that contribute to greenhouse gas release have also conferred major changes in land use globally. And this often looks like the clearing of natural forests, grasslands, or savanna systems for intensive agriculture or development. And one piece that comes along with often land use change is habitat fragmentation, which can reduce the functional population size of lots of different taxa and has contributed to an increase in the rate at which species go extinct globally. And so this real and happening kind of challenge of biodiversity loss is really quite intricately coupled with the broader challenge of global climate change because many of the activities and processes that result in kind of community homogenization. A clear example of this is the transformation of a grassland to a cornfield, for example. We have a much less biodiverse community, and we also know that in many cases these communities that have lower biodiversity are less able to buffer the effects of ongoing fossil fuel combustion. We know a lot about how biodiversity affects ecosystem function actually from experiments. And so this is a photograph of the big biodiversity experiment at the Cedar Creek Long-Term Ecological Research Site in central Minnesota. This experiment was started in the mid-1980s. And the basis of this experiment are these 9 by 9 meter plots that were planted and have been maintained with communities of differing biodiversity from 0 to 25 different species. And we've learned a lot about kind of the functional role of biodiversity from this experiment. But one thing that we can think about is when we kind of picture a grassland is that taxa coexist within communities through what the ecologists call niche or resource partitioning. And you get a good picture of that below ground. Grassland taxa have really diverse root morphologies, which allow them to play very different functional roles within ecosystems. And in plots where there are larger numbers of taxa, they're able to better exploit and more efficiently use the resources available to them. And that confers increases in production. They grow more plant biomass, and they transfer more of that biomass carbon to slow cycling soil carbon pools. It's not always just a production story, though. Communities that are more biodiverse are also more resilient to stress events like drought years, and are also more resistant to interruption by introduced pests and pathogens. So any of you coming from the Midwestern United States are probably aware that many municipalities really favored ash trees as municipal street plantings throughout the 60s and 70s, which was very nice for a long time because the trees grow quickly and uniformly, but the spread of the emerald ash borer over the last couple of decades has in some cases led to near complete mortality of residential forests in many communities. And with it brought along the loss of all of the additional benefits of having an urban forest, from climate regulation to carbon storage. In response to this, some municipalities, this is a photo from Minneapolis, have instituted policies to diversify urban street tree plantings and make our communities more resilient to ongoing stress events and any future introductions. And so collectively, biodiversity really influences both the resilience of communities as well as their capacity to store carbon. And going back to the experiments at Cedar Creek, the effect of increasing biodiversity, so the blue lines in this figure at the top, actually outweigh the effect on production in comparison to giving plants more nitrogen fertilizer or actually increasing the amount of CO2 in the atmosphere. And so these are kind of challenges that we need to be thinking about in concert with one another.
Thank you. Thank you, Allison. And now for Bill. In its comprehensive research, the United Nations Intergovernmental Panel on Climate Change, of which you were a member, has identified the consequences of warming in excess of 1.5 degrees Celsius at the end of the century and the urgency of bending the path of global greenhouse gas emissions to avoid the worst impacts. Could you summarize these findings?
I'll give it a try. I'm going to have to stand up here because I can't twist around it like I used to. Climate change is already here, and most of you recognize that. And certainly this most recent situation here with the fires in Quebec. This is just taken a couple of days ago in New York. This is here to remind those of you who are looking for oceanfront property that this may not be a good idea. And this is another one right here, 162-mile-an-hour hurricane just last fall. So it's really, it's here. This is not skepticism at this point. The original climate goal, which every country in the world has agreed to, is to basically achieve a concentration of greenhouse gases in the atmosphere that will avoid dangerous anthropogenic interference in the climate system, 1992, in Rio. You may remember the Rio summit. It took until 2015 for governments to decide what dangerous meant. And what they concluded was that it should stay, the temperature should not rise more than 2 degrees Celsius. That's 3.6 degrees Fahrenheit for those of you who are metrically challenged, as most Americans are. Then the small island nation said that's not enough, and so every attempt must be made to keep it below 1.5 degrees. Of course, governments had no idea how this was going to happen, so they turned to the Intergovernmental Panel on Climate Change, which is a group of it's every nation in the world is a member, and each government nominates scientists to assess and report back to governments and the public the status of climate. And so that report came out in 2018, and it very simply said, to achieve temperatures, to prevent the temperatures from rising excessively, global net anthropogenic carbon dioxide emissions must decline by about 45% from 2005 levels by 2030, reaching net zero around 2050 and net negative thereafter. That last phrase is usually forgotten, and we get a lot of misunderstanding about net zero. It just means that at that point, our emissions will be no greater than what nature can take out. Allison, thank you for setting that up on that part. That the natural world is removing over half of what we put in every single year. And so what we must do is simultaneously reduce our emissions and hopefully increase the removal rates. And that's the plan. So how do we do that? Well, we build homes like this. Both Hank and I have built homes that are essentially net zero. We're connected to the grid. We produce more with our solar panels than we use from the grid at night and so on. And all three of us actually drive electric vehicles. Hank and I are able to charge ours partly from our own homes. So, and then you provide that, and so we're providing the energy with, use as little as energy as possible, and then provide it with zero carbon. How are we doing? Well, this is what the Intergovernmental Panel on Climate Change said in their latest report from last year, and it doesn't look good. This line up here here's the historical ones. Here's where we are. And we've promised to do things that will keep us on this line. This is where we have to be to stay below 2 degrees. This is where we have to go to stay below 1.5 degrees, out to 2100. And it's clear we're nowhere close. So we need to up our game. This is just a figure that illustrates the way things are working. These are the emissions from fossil fuels. These are the emissions from deforestation. Together, they're 10.8 billion tons of carbon dioxide. And yet the increase is only 5.2. I mean, that's like magic, right? That's not the kind of math I learned with something's missing here. And what it is the plants on land are removing about 3.1 billion, and the ocean's about 2.9 billion. And so if we could up these removal rates, this is going to be harder to do, but they're discovering that planting more kelp forests is removing additional amounts of carbon dioxide. Here, it's a combination of things. And here's what the latest IPCC report said. We must safeguard biodiversity and ecosystems fundamental to climate-resilient development. All right, in the past, it's all been about technology. Suddenly, it's about ecology. Recent analysis suggests we must have effective and equitable conservation of approximately 30 to 50% of Earth's land, freshwater, and ocean areas, including currently near natural ecosystems. High confidence. Boy, when the IPCC says high confidence, if you've ever had a group of scientists trying to agree on anything, you know that is real. And then this phrase appears elsewhere. It is also the case that protection of existing natural forest ecosystems is the highest priority for reducing greenhouse gas emissions. And they quoted my paper. I couldn't believe it. So why is this? How do we get big trees and more forest? And you know, we could plant more forest, but little trees don't absorb much carbon dioxide for a very long time. And I and a bunch of other colleagues have been working for the last 10 years and demonstrating that because US forests only average about 50 years in age, that means these are species that can live 300 years. And we do that because it's all been about harvesting. And sustainably harvesting means we keep all the trees younger than 50 years. And so if we let the trees grow, they pack in huge amounts of carbon. And a study came out in 2018 showing that in 48 forests around the world, that half of all the carbon in those forests, if they're multi-age, mature forests, is in the largest 1% of trees. Big trees matter, and we don't have many big trees left. So if we can have some more big trees, which are half carbon by weight, then in these forests, we will keep the carbon we have, and those trees continue to remove carbon. This is a fact that was overlooked because we'd cut so many trees, we didn't have any old trees to study. And so the forestry industry kept saying, well, we have to plant more young trees, and we'll just take down all the big old ones. So, So basically, we have two routes here. One is that we all use as little energy as possible, use what energy we need to use, have it come from zero carbon sources, and let's protect more of our natural systems. It's not only forest, as you also heard, it's grasslands, it's wetlands. All of these systems, some of which wetlands are called wastelands by most people, but they are hugely important, both biodiversity and in terms of climate change. So it's a two-pronged approach, which gives us more chance to meet our goals. Thank you.
Thank you, Bill. And now for Tom. Back in the 1970s, Congress responded to the severe problems of water, air, and waste pollution. These days, the legislative and regulatory processes are failing to decisively address climate change. What's gone wrong? And are there lessons from the earlier experience to set us right again?
I guess the first question you are all asking is why, with the amount of science that we have supporting our understanding of the dynamics of climate change, why hasn't the Congress acted? And I don't have an answer to that question that's any better than any of your answers to that question. But I might say that while I might make what might appear to be a statement that reflects some partisanship, I will remind you that when I worked in the Senate staff back in the 1960s and 70s, late 60s and early 70s, I worked for Republicans. Some of you are old enough to know some of those Republicans. John Sherman Cooper was my patron. Howard Baker was the ranking member of the subcommittee, and Caleb Boggs was on the committee from Delaware, and Bob Dole from Kansas was also on the committee. So we asked the question, why, with an unbelievably less amount of scientific underpinning regarding air pollution and water pollution, did the Congress enact the Clean Air Act in 1970 and the Clean Water Act in 1972? Is there anything there that suggests why Congress hasn't acted? As I said, it's a question that all of us have to confront, and we need to ask ourselves questions and what we can do to do that. Now, I'm going to talk mostly about the federal response. That doesn't mean there aren't other levels of response. Some states are doing very innovative things. Some local governments are doing innovative things, so that there is some acts of progress even in the private sector. But the question is, we need a comprehensive legislative response to the issues of climate change if we're going to respond to the challenges that Mia, Allison, and Bill have presented. And when we look at that, let me see if I can run this. I should say that the class of '73 holds a special place in my heart because I came here in the fall of '72, so the Center for Environmental Studies students in '72, '73, the graduates in '73, had to experience my learning experience as a teacher, and they had to bear that difficulty. The advance, there we go. If we start with the question of what kinds of processes do we have available for a public governmental response, this graphic sort of tries to lay out the process. It starts with problem identification, then we follow that with a congressional legislative response. It takes 1 to 2 years. It has to take less than 2 years because each Congress ends at the end of 2 years, and if you haven't done anything in those 2 years, you have to start all over again in the next Congress. So then the agency receives authority from Congress to do something. Then we go through judicial review, implementation, and enforcement. It's a very extensive process that takes from 6 to 15 years from beginning to end. For instance, we're still writing new regulations under the Clean Air Act of 1970. And so that gives you some sense that public policy is a difficult process and one that doesn't produce instantaneous results. Because of frustration with the fact that Congress hasn't acted, EPA has attempted to sort of start the process where we have here in this agency. They've attempted to write regulations under the Clean Air Act to address some aspects of climate change, primarily the combustion of fossil fuels in order to produce energy. They tried this at the beginning of the Biden administration and moved somewhat through the regulatory process, but the Supreme Court was so eager to address and knock down that effort that and the issue was not yet ripe for review, the Supreme Court stepped in and said, no, EPA, you cannot do that, and knocked out that effort. Subsequently, and just this last May, EPA has attempted again to write a regulation dealing with fossil fuel generation of electric energy, and has initiated another rulemaking process, and that process is just beginning, and it would take usually something on the order of 1 to 5 years to get a regulation through the whole process. So we're seeing another effort. They did get some help from the infrastructure legislation that was enacted that attempted to overcome some limitations that were placed on EPA by the Supreme Court. But we don't have a comprehensive program. And so the question is, why did the system work in 1970 and 1972 to produce durable and still very effective legislation? And it begins at that very early process, problem identification. Notwithstanding everything that you've heard and the amount of science that supports climate change is orders and orders of magnitude greater than the amount of science we had available in 1970 for the Clean Air Act and the amount available for us in 1972 on the Clean Water Act. So even with that amount of science, what is it that's causing the problem? And it goes back to the beginning. We can't get agreement across party lines or even ideological lines that there's a problem. Notwithstanding everything that was summarized by these three folks and the thousands and thousands of folks just like them, we cannot get that first step. In 1970, Senator Muskie would bring the committee together, and his first question was, should we together work to address air pollution? And they held discussions on that question, and until he got agreement from both sides of the aisle that there was an issue that needed addressing, did they commence the legislative process. So we can't right now get past that first step. There are more more climate change deniers on the committee that I served than there are people who are concerned with climate change. So that's the first step. Now, the obvious answer to that is elections matter, and we've probably, and I'm sure others have heard same kind of questions, but whether you're interested in climate change or other major issues facing the country, the 2024 election is going to be the most important election, certainly in my lifetime, and I think in maybe historical terms. What does it take to do this? If I can find the next slide here. This is the normal legislative process. It takes work. The normal process is a bill is introduced, the parliamentarian refers that bill to the respective committee's jurisdiction, and then the process begins. It goes to the committee, there are hearings, there's markup, reported to the floor, debate and amend, first through the Senate and then through the House. To give you a sense of how much work was involved in the Clean Air Act, when the committee initiated the process, the committee held 30 days of hearings on clean air, or on air pollution. That meant that most of those 9 members of the subcommittee sat through 2.5 to 3 hours of a session, and they did that for 30 days. That kind of commitment of members to that process. Now they don't have hearings very often, and when they do, there's usually only one member of the committee in attendance. So they had 30 days of hearings on clean air. They had 33 days of hearings on clean water a year and a half later. In the markup session, the markup is where the members actually sit in a very small conference room, and I might add, it was a smoke-filled conference room. I was the only person that did not smoke in this very small conference room. And for 2 hours to 2 to 3 hours each time, they would deliberate on what the actual language of the legislation would look like. In those markups on air pollution, they held 20 days of such markups. Again, a commitment from members to understand what the legislation should be and could be, and the work necessary to craft the legislation that would, in effect, address the problem of air pollution. It then goes to the floor. We had a unanimous vote, 96 to nothing, on the floor. And that wasn't because there wasn't opposition from members. For instance, the auto emission standards were very controversial, but the members of the Michigan delegation refused to even address amendments because they knew that the committee was together, both the Republican and Democratic members, and that they knew their legislation inside out, and any effort to overcome that was doomed to fail, so they didn't even try. The bill then goes to the House of Representatives. The House acted after some time. Then it goes to conference committee. This is where the two sides, the House and the Senate, reconcile any differences between them so that the same legislation would go through both chambers. On air pollution, we had 6 days of conference meetings. These lasted usually, again, 2 to 3 hours. A commitment from the members that it was necessary to accomplish that task. That kind of commitment from the members does not exist in the current formulation of Congress, and until it does, I don't think we will see any comprehensive legislation addressing climate change. So my basic conclusion is relatively negative. I just don't see the current dynamics producing the kind of legislative response that not only this country needs, but the globe needs in order to address climate change. I suspect there might be some questions that I've suggested here, but I think you get the picture. Until we get the kind of legislators that I worked for in Congress, we're not going to see any real progress.
Thank you, Tom, for that happy note. We're now moving to actually a discussion amongst the panel members, and continuing on the question of Congress. Congress recently passed legislation which aims to replace fossil fuels with clean electricity, but the proposed measures will likely fall short of even the administration's emissions reductions goals over the next decade. What additional strategies and policies do you believe are crucial to limit the greenhouse gas emissions over the next 50 years? Anybody want to jump in on that one? I think all your mics are hot.
I'll take a crack at it. When the government doesn't act, the alternative is for the people to act. And anything that you can do to make a difference is critical. And what often happens is, as some, I forget who it was, I think it was Amory Lovins once said, when the people lead, their leaders will follow. And I think that's really maybe what we have to do. That's certainly been behind my motivation and Hank's motivation and Tom's motivation to do what we've done. And what I find is people are curious about a house that doesn't, that generates more energy from its own panels than it uses from the grid. And sometimes they come back and ask for more information. And some people go off and then do something similar. You don't have to go as far as we did, but there's so many things you can do if you're in an existing house to make it more efficient. And one of the biggest things that happened technologically was changing light bulbs. I mean, when we went from 100-watt tungsten bulbs to the compact fluorescents, which were not so great in terms of the color rendition, I'll be frank with you, but they used about one quarter of the electricity. Then along came the LEDs, which after a bit of tuning, the first ones were terribly blue, they use 1/6 as much as that 100-watt light bulb. So scour your house and see if there are any light bulbs left to change. That's the very first simple thing you could do. And the other thing is, of course, tightening up your house so that it doesn't leak air, which makes it uncomfortable and makes the furnace run longer. And then, of course, the latest thing is to shift away from furnaces to heat pumps. And those have now become good enough that even in colder climates, they work. We use a ground source heat pump, which means we don't have to worry about the outside air temperature because it's the temperature of the ground that we're heating up from. And but the air pumps now can go down well below freezing, down to near zero apparently. And then you may have to use a little bit of just electric resistive backup. But the technology has really moved remarkably rapidly. And then the other thing to do, as Tom says, is become active politically. And what you can't do at the national level, you can do at the state level. Massachusetts is like California, is taking a lead. Our new governor is going gangbusters. I spent 3 hours yesterday on a commission meeting about what we're going to do about our forests so that our forests will be able to accumulate the right amount of carbon over the next, between now and 2100, to help us meet the goals. We are for all kinds of subsidies and benefits for people who get heat pumps and get solar panels and everything. What you can't do at the state level, you can do at the local level. We have a net zero committee here in Williamstown, started by citizens, and they have meetings and they all put out what can be done and try to inform their fellow citizens of what can be done. So I think maybe it's a multi-pronged process. We can't wait for the UN to solve the problem. We can't wait for the US government to solve the problem. And so we just have to get on with it.
Mia?
So when the report came out a few years ago that in order to avoid the irreversible and catastrophic consequences of climate change, we had to limit warming globally to 1.5 degrees. And it became obvious that we would not only have to reduce emissions and bring emissions to zero, we also probably had to come up with methods of removing CO2 from the atmosphere that's already been emitted. And so in the last few years, there's really been an explosion of interest in both developing the technology for direct air capture of CO2 and also researching the natural systems that Allison mentioned that take up carbon dioxide in the ocean and on land to see whether we could manipulate those systems to make them take up more CO2 than they would if we did nothing. And so it's sort of like a Wild West right now. There are companies springing up, attracting a huge amount of funding to research these processes and try to figure out which methods work. In fact, you can right now buy quite dubious carbon credits that are based on untested technology, some of which are actually quite nonsensical if you study the carbon cycle. And so it's actually a really interesting time right now. Some of these technologies that are being worked on right now are probably going to be ones that are important in the future. And there's a lot of work being done right now to understand how much CO2 these techniques can potentially take up. In the ocean, for example, there's a lot of interest in growing kelp, not only for alternative animal feed or for human food source, but also as a carbon sink. There's also research being done on ocean alkalinity modification. So can we change the chemistry of the ocean in a deliberate way to make that water take up more CO2? And I think Allison probably could comment more on techniques that are being investigated on land to enhance carbon uptake.
Yeah, so I totally agree with Mia that a reality is that some level of carbon capture is going to be critical. In part due to the latency associated with what is going to be a massive change in infrastructure associated with heating and cooling, as well as the ongoing kind of carbon outputs associated with shipping and jet travel. There are a variety of burgeoning industries associated with this carbon capture question. And I think one big challenge kind of moving forward will be like true validation of the nature of both the carbon capture and how stable those different carbon pools are. I think there's a lot of kind of certainly even with the kind of buying tree planting offsets, like there's currently not a lot of longitudinal tracking of, for example, how many of those trees actually survive. I think in terms of policy, another place where we can be thinking about kind of tweaks there are some places where some changing incentive structures could be quite helpful. One of those places is agricultural subsidies. There's huge benefits of changing major components of our diets, but there are aspects of the way agricultural subsidies are currently structured that don't kind of enable the full kind of, even if we individually make choices about the food that we eat, and there's been a massive reduction in dairy consumption, but the structure of agricultural subsidies don't fully kind of convey the full carbon benefits of those personal choices. And so changing some of those incentive structures, that would be a policy shift and comes with the challenges of making policy, but would be very helpful from a carbon balance perspective.
Any other comments amongst the panelists?
Let's get the audience involved.
Well, we will in a moment. We will in a moment. Okay, another question for the panel, and then we will turn it over to open the floor and have participation from the audience, is climate change will most harm countries who have the least role in causing it and are often least able to afford mitigation and adaptation. In light of these circumstances, how can we secure the participation of all countries necessary to avoid the worst impacts of climate change?
As the chemist who ended up at a School of International Relations, I'll try to answer that question.
Again, validation of the liberal arts.
Yeah, advantage of liberal arts education, absolutely. The United States still has the largest amount of carbon dioxide in the atmosphere historically. In other words, we have added the most of any country in the world. Today, every year, China is putting in twice as much as we are. China, of course, we have a population of whatever it is, 360 million, and they have a population of 1.3 billion, 1.4 billion. India is now just past China in population. India is much poorer than China, and and China did this. It's a miraculous pulling. They say 500 million people out of poverty, but that came at a cost in terms of massive uses of fossil fuel energy. China is also the biggest producer of renewable energy and the biggest user of renewable energy, more than we are. Wind power, solar power, hydropower, and yet they're still building coal-burning plants because they need more energy to kind of keep the system going. A small country, I mean, I've done some work in Africa, in Ghana and Kenya, and these countries, I mean, their emissions are minuscule, and even as they're developing, they're minuscule. What's great to see is that, particularly in Ghana, they're not racing to become a fossil fuel dependent society. In Kenya, the state electric company was so slow at getting things out that a group of non-governmental organizations started a program of installing solar panels. They had these. There had a whole group of barefoot women going out and installing solar panels in these villages. I'm really not worried about the emissions that are coming from those countries. I'm worried about the emissions that are coming from Europe and North America and China, and to a lesser extent Japan and Russia. And unfortunately, the Europeans have decided that they have a directive, which is to be 100% renewable electricity. And so how are they doing that? Well, 60% of their renewable energy used in Europe is from burning plants, primarily trees from North America. To get the same amount of electricity from burning wood as from burning coal, there's more carbon dioxide released if you burn wood to get a kilowatt hour of electricity than if you burned coal. And then you've lost the capacity of the trees that were cut to absorb the carbon dioxide. And I've been very involved with Europe for the last 5 years. I was even invited by the Parliament to be there for a big presentation in December. And even the Vice President still falls back, well, we have to be 100% renewable. What about the carbon? We have to be 100% renewable. What about the carbon? We have to be 100% renewable. I mean, it is just astounding. It's not just our political leaders who are dense on this issue. The European ones are as well, because they're locked into a plan that they're not willing to change. So I think we just, you know, I think we put all our effort into the G7 or the G20 or something like that. That includes some developing countries. And let's see if we can't get some agreements outside of the need for universal, all 190, whatever it is, 6 countries. That's impossible. Let's see if we can't work with these smaller groups that are the biggest problem, like us.
I think one challenge that we need to keep in mind in the context of this is that although many poorer countries are not major historical emitters and are maybe not even on a fast track to becoming strong emitters themselves, their future climate is contingent on our historical emissions and our future emissions. And so we also have a responsibility to help them manage the externalities that they experience associated with climate change. Many of these countries are in areas of the world that are going to experience the most extreme weather conditions that are going to confer drought and increasing political instability in these countries. And I mean, if only from our own self-interest, helping the people who live in these places live manageable lives is within the interest of our own institutions and something that we really have to have forefront as we consider not just how we reduce greenhouse gas emissions, but help these countries kind of move forward into our new climate regimes.
Okay. I was just going to say, I think that is important to to help them make the why should they crawl and then walk in an energy transition? Why don't they just stand up and walk with the other side of the energy transition? In other words, they're going to be spending the money anyway. India canceled, I forget how many big coal plants when they realized that solar, the huge solar fields would provide the electricity at a fraction of the cost, and that takes some management. The grids in India aren't all that great, but they'll get better if they have the opportunity to do so and see a way of doing it.
And at the same time, we have a lot to learn from the developing world as well. In terms
yes.
of how to interact with the environment in a
Yes,
sustainable
that's for
fashion.
sure.
So at this point, I'd like to open it up to the audience for comments and questions. And if you could yell loudly so that I can... One moment. So if you could speak loudly so I can hear it, I'll try to repeat the question and not get it all messed up. And if you could direct it at one or more of the panelists, that would be great. Are there questions from the floor? Yes.
Yeah, Professor Moomaw just mentioned India, and am I wrong? Wasn't it in the last 2 weeks that India is opening up 6 coal plants?
That's probably
The question was, is it true that India is opening up 6 coal plants?
I hadn't seen that exact number, but yes, I know they are opening up more. All these but it's not that they just decided to open them. These have been in the plans for probably 10 years. And, you know, once you start on that, it's kind of hard to turn off the spigot.
One other thing. Has there ever been a study on NASCAR?
Has there ever been a study on NASCAR?
Yeah, the we have people go, 100,000 people go to watch cars go around in circles and burn up in the atmosphere.
Well, my guess, if I can handle that one, is that probably the people going to NASCAR are burning more fossil fuel than the NASCAR drivers as right there. So, other questions? Yes.
Actually, let me add,
One second.
if they would allow electric cars to compete in NASCAR, there would not be any
They would all win.
fossil fuel cars.
There actually is an EV NASCAR equivalent, and they don't allow EVs to compete with NASCAR because they just wipe them out. The EVs are just so much faster and better.
If any of you have electric
So we may
vehicles,
solve the problem that way. It's just not as good.
you can testify that it's really easy getting a speeding ticket, and it's also really easy getting on the superhighway because you have acceleration you just can't believe. Yes.
This is probably for the whole panel. Given the sort of pessimism on some of the policy issues in particular, there have been some more like drastic scientific recommendations about like geoengineering or climate intervention, which seem pretty fraught scientifically and ethically, but also feel increasingly like, what else do we have? I just wonder if you could give your perspectives on the dangers, the benefits of those types of options.
So the question was to deal with massive environmental engineering, changing the ocean and atmosphere by technological means. For the whole panel.
I can give it a try.
Put your mic up.
So I would say that 2 geoengineering strategies that have been discussed and discarded are altering aerosols in the atmosphere, seeding the atmosphere with the kinds of aerosols that occur naturally but cause cooling. One side effect is that they also cause acid rain. And so, and I think that it was promoted actually as a realistic, potentially realistic stopgap measure. So if we can artificially cool the atmosphere by enhancing these aerosols, it could give us some time to get our act together, reduce emissions, maybe develop other ways of mitigating the climate problem. But you can see the problem with that. You know, the stopgap measure has a lot of collateral damage. And if you give people a little bit more breathing room, it may de-incentivize the development of the alternatives we need. Another method that was proposed was ocean iron fertilization. So there are vast areas of the oceans that leak CO2 to the atmosphere naturally. And one way you can reduce that leak is by seeding the ocean with iron, which is a micronutrient that's missing. It's like a vitamin that's missing. So phytoplankton can't grow and take up the CO2. And so there were a series of experiments done starting in the 90s to see, is this a realistic possibility? Because there was a lot of evidence emerging that the reason ice ages were cold was because CO2 was lower naturally at the time. And the reason CO2 was lower was because that CO2 got trapped in the ocean because the ocean leaked less CO2 to the atmosphere. So could we make that happen artificially in order to help the climate problem trap CO2 in the ocean? But there are there are a lot of unknown impacts on ocean ecosystems of making such a huge ecological change deliberately, and those are poorly understood. In addition, it was found that the CO2 that was taken up by phytoplankton from the iron fertilization did not actually stay in the ocean. It got recycled too quickly and the CO2 came out anyway. And so there are places you can go in the ocean where it would be moderately effective, but the impacts on ocean ecosystems that are already stressed by warming and ocean acidification is just too unknown. So it's an interesting scientific question to pursue, but it's actually not one that's regarded as a realistic option for the future, especially since the ocean provides a huge amount of the food that we consume, especially in developing countries. In many places, like most of the protein that people consume comes from the ocean. And so manipulating these already stressed ecosystems seems like a bad idea. So it's no longer considered realistic. I would say that things that are more realistic have to do with protecting the carbon sinks that already exist, preventing them from being degraded and reducing their ability to take up carbon. And so coastal areas, terrestrial areas that are currently carbon sinks, we can have a lot of bang for our buck, I guess, by focusing on conservation and protection of these areas and restoration of those habitats that have been degraded.
Yes.
There's been concern about the fallibility of renewable energy, and I was wondering if any of the panel would promote using nuclear energy, either fusion or eventually fission. Fission and eventually fusion as a bridge anyway to reduce carbon production.
So the question was whether there is potential for using nuclear energy, either fission as we have now or fusion as we hopefully will have in the future, and what some of the environmental issues are there. Bill?
I think that we should certainly keep all the nuclear power plants we have now going as long as we can do it safely. One of the reasons it's not a near-term solution is because it takes 10 to 20 years to build one. You know, it takes a very long time to build a nuclear power plant. We still haven't solved the waste problem. As we're seeing in Ukraine, it is not such a great idea if you're at war to have nuclear power plants, right? It's a huge vulnerability. And so I think Germany was foolish to shut down all their nuclear power plants before they had all their renewable energy in place. And what that's meant is their emissions have gone up because they've gone and dug more coal, destroying villages in the eastern part of Germany to get it, creating political problems, obviously. So I think what we're seeing is China is the main builder of nuclear power plants today. Just as with everything else, they can build them faster than we can. Korea is the other source. We actually do not have the capacity in the United States with the senior people anymore because we have not been building nuclear power plants now for, well, we just canceled one of the two that we were building. So we just have economic problems, we have organizational problems. So there's a whole move to go to modular, smaller plants, and I'm interested to see whether that'll work. If it does, that would be great. Those could be built in a factory as opposed to on site and then trucked to a factory or something. So for me, there's a role for nuclear because of its carbon neutrality, but I don't see it as an expansive role. And as for fusion, don't hold your breath. I mean, fusion has been in the next 10 years since I was about 6 years old. And it's still this way. And that great event, right? It was a great event scientifically that you got more fusion energy out than you put in from the lasers. What it doesn't count is the amount of electricity it took to run those lasers. That's not in the calculation yet. So and it was for like a nanosecond. We have 60 cycles. 1 nanosecond every decade is not going to be an operational system. I'm skeptical, as you can tell.
So there's a question back over here. Oh, right here. I'm sorry.
A two-part question for Professor Moomaw. I'm involved in land management and land use planning for a 20,000-acre privately held forest in eastern Pennsylvania. And one of the groups we're working with is the Rough Grouse Society. And they maintain that we have 90% mature forests. They maintain that, and also the Department of Conservation and Natural Resources in Pennsylvania, they maintain that cellulose production, which is equivalent to carbon capture, as I understand it, is double to triple in a multi-stage young stem-dense forest than it is in a mature forest, which would run counter to what you said. Can you enlighten me?
The question was dealing with the rate of carbon uptake in a multi-aged younger forest versus an old-age forest.
Well, that's an argument often made by hunters and others who want to shoot birds that are in those early stage forests or in timber companies. If you look at the growth curve of forests, and let's say you take decadal measurements, if you were to say, okay, we're going to cut down these old trees that are 100 years old and replace them with fast-growing younger trees, it might be true that they would absorb more after about 50 years than the ones you cut down. But what about the emissions that came from cutting down those older trees? Those new trees will never hold as much carbon as the older ones did until they get to be that old. So it's not an argument for, the goal is to store carbon, have as much of it in the trees as possible and in the soils of the forest. And the simple-minded way of thinking about this, carbon that's in a forest is, or in a grassland, is carbon that's not in the atmosphere. And the rate is just a means of getting there. But if you're already there, why take it away? Would you, if you had a bank account with $1 million in it, and you said, but I can get higher interest on a bank account that has $10,000 in it, would you get rid of the older one and start with the new one? I don't think so. This is the problem.
Other question in the back, the blue.
Yes, I have a question really in 2 parts for all of the panel. What would the panel recommend in terms of carbon capture and subsequent sequestration for countries or states that do not have forests or very few forests? And then secondly, what is the role, in your opinion, of sequestering inorganic carbon as opposed to organic carbon, particularly in an industrial setting or microbial setting?
So the question is, what are the opportunities for countries that don't have forests in terms of sequestration and carbon capture? And then the second was the possibilities for industrial inorganic carbon capture and sequestration.
Yeah, so forests certainly get a lot of publicity in terms of opportunities for carbon capture. Planting trees is a very tangible kind of activity. Grasslands actually have massive carbon pools, particularly in their soils. They have very deep soils that contain a lot of carbon, and soil carbon pools cycle slowly relative to plant biomass pools, even in forests. It's another reason why protecting old growth forests is critical for larger kind of carbon sequestration purposes. And so places without forests are often many of our more savanna and grassland systems. One challenge about communities in these places is that these are also some of the terrestrial environments that have been most effectively degraded. It's much easier to do agriculture on land that was previously a savanna or a grassland than it is a forest, just from a practical perspective. The deep soils are also highly nutritious. And so moving some of these systems back from row crop agriculture back to perennial plants has pretty major potential for carbon sequestration. And there's been a lot of work, for example, even on perennial crops such as kernza to try to make grassland systems or return the capacity of some more degraded grassland systems as carbon, for the opportunity of carbon storage. Wetlands are also play a sort of outsized role relative to their spatial area within the broader carbon storage component. Do you want to talk about inorganic carbon?
So there are some efforts made to study uptake of CO2 from the atmosphere by accelerated weathering of rocks. And so one natural process for taking up CO2 is just rock weathering. So, CO2 dissolved in rain falls on a rock and very slowly dissolves that rock. And that actually converts the CO2 into a chemical form where it won't exchange back to the atmosphere. And so if we look over the next 100 to 200,000 years in the future, this is how anthropogenic CO2 is going to go back down naturally. This is how the carbon cycle will recover, and it's from the silicate rock weathering. And so geologists who have this long view say, oh, okay, can we just take that process and make it faster? And there are ways to try to do that. You can take the rocks that are the most reactive, and you can powder them, and then react them with CO2. But again, these efforts, these are really creative, novel efforts, but a lot of them are just in development. None are operating on an industrial scale, but I'm looking forward to the next couple decades of some breakthroughs in this front, but we're not there yet.
Okay, I think it's come to the time that we have time for one more question.
That's all.
Right there. Oh, somebody's had their hand up for a long time. Oh, you're in the shadows. Yes. Please.
Former student of yours, thank you very much for moderating this. I wanted to end this on a note of something that we can do. We have all these alumni here. What can we do to encourage Williams College to work with students to divest from fossil fuels, not only in terms of stocks, but also in terms of physical plant investments, like not building more underutilized parking garages?
Well, let me let me just jump in there and say that the college does have a plan to decarbonize. I am currently serving as the Sustainability Projects Manager at the Clark Art Institute, coming off the bench and doing that, and I've had interactions with the college sustainability planners. One of the biggest challenges in becoming 100% electric is our infrastructure in Williamstown is not sufficient to do that. So we need to, as been suggested by our panel, actually get involved with the regulatory and the political activity to make that one of the highest priorities of enabling, not just have people convert to electric cars and electrify their homes, but if everybody did that tomorrow, the grid would just collapse. So we need to actually be investing in the future in actually being able to accomplish that with an infrastructure. But I will let the rest of the panel grab that hot potato and run with
Yeah,
it.
I can comment. So the college just went through a large strategic planning process, and one of the pillars of the strategic plan that emerged is sustainability. And so there actually is a lot of initiatives the college is underway to reduce the carbon footprint. For example, one of the biggest sources of emissions on the campus is the cogeneration plant. It's a gas-fueled plant that produces steam to heat our buildings and also produces electricity in the winter. All the bought electricity that we use on campus that we don't produce is already carbon neutral. There's a solar farm that the college has invested in to achieve that goal. Another axis that's really difficult to achieve carbon neutrality on is travel. There's a lot of travel associated with our business of educating students. And there's students not only traveling to our campus and back to their homes, there's also study abroad. There's also travel for athletics. There's wonderful field and experiential courses that involve travel. There's travel associated with us bringing our students to professional conferences. And so the carbon, until travel becomes not dependent on fossil fuels, those are sort of critical parts of our academic mission that require carbon emissions. And so something that the college is working on is researching carbon offsets, trying to figure out the most just and equitable and effective and real and measured ways to actually invest in buying offsets for emissions that are associated with things that we cannot change yet. And so there is a plan. It's on the strategic planning website if you want to read more about what the college is doing on these questions.
Are these I have a question. Are these, I hope these are not getting somebody else to plant some trees offsets, that these are actually energy production offsets where you're producing electricity. Williams is paying to produce solar electricity somewhere else. Mm-hmm. That's the best way to do it. Mm-hmm. These forest offsets sounds like a great plan, great idea. But, you know, recently California discovered 90% of their offsets are not real. California's been leading the way. Mm-hmm. And they found that they just are not, they cannot verify 90% of them as actually offsetting anything. So Microsoft lost, I forget, $100 million worth of offsets in a fire in California. What do we do about that? So we need a better system. And in terms of Williamstown, part of the state plan that is being developed right now will look at what is the right balance, the best balance between locally generated people with their own solar panels and their own batteries connected to the grid, which means that the grid will not be carrying as much as it is now, because a lot of what you use right there. It never goes to the grid. And this is one way to help beat a grid that's inadequate, is to have more on-site generation and storage. And the utilities are now paying people to have storage that they can access during peak times. But of course, solar is great in the summer because it's when peak air conditioning demand, that's when you do it. When do you draw from the grid? At night, when there's less demands. It really is a nice combination. So we need to think about it in terms of the conceptual structure as well as the pieces of technology themselves.
Okay, with that, I think we've gone over and we started late. So I want to thank the panelists.